Hello, I'm Andrew Heward, and I'm a PhD student with the Perceptual Engineering Lab at the University of California, Santa Barbara. This presentation provides a demonstration of a new pipeline for passive haptic feedback. Our pipeline engages the user's haptic senses and improves the sense of presence in virtual reality applications. Let's get started. What is presence? Presence is the sense of being there in the virtual environment. In social VR, presence is the sense of being there together with others. It includes spatial presence, or whether the virtual environment matches reality. It includes self-embodiment, or whether the virtual avatar feels like the user's body. It also includes the physical senses, such as sight, sound, and touch. Presence also includes social interaction, or whether the user feels like others are there together with them. Social presence can be enhanced by showing natural movements to remote users. Passive haptic feedback provides the most natural physical interaction possible, using the hands to pick up real objects instead of interacting through controllers. This work aims to enhance presence in VR by engaging the user's haptic senses. We created a pipeline, which we call CardsVR, for passive haptic feedback using a deck of 52 playing cards. Players interact with physical cards by picking them up, holding them, playing them, or moving them, with one-to-one correlation between the physical and virtual environments. This work provides several key contributions. This pipeline is the first application of passive haptic feedback we are aware of that allows two or more remote players to play a game of cards together. This pipeline can track hundreds of objects with a high frame rate. It achieves this due to the simplicity of the pipeline. We also performed a user study to evaluate the impact of passive haptic feedback on the sense of presence. Our pipeline uses flat fiducial markers to keep track of initial card locations and correct static objects in the environment, such as the virtual table height, for improved spatial presence. After the game begins, we turn off the tracking system and instead use the VR headset's built-in hand tracking to facilitate card movement. This avoids the added complexity and latency of implementing a Kalman filter to reduce tracking jitter, which can distract the user and reduce their sense of presence. An external camera was installed on the VR headset to track card locations. Our implementation uses a custom iOS app and the Photon Network's real-time engine to pass sparse marker data to the headset over the internet. A symbol library consisting of 3,000 Uruko markers was used to represent 52 playing cards, each with 28 symbols per side. We needed at least 2,912 symbols to represent a complete deck of cards. Marker 3D reconstruction was performed using OpenCV's infinitesimal plane-based pose estimation, IPPE, which requires markers consisting of 4 sides and was found to have the least jitter. Although the markers are initially 3D reconstructed at the camera far plane, we correct for depth by factoring in each marker's physical size. The size of the markers are unique and known beforehand. A lookup table provides an offset vector between the marker center and the corresponding card center locations. Continuous tracking was attempted, but it suffered from positional and rotational jitter that we found to be distracting and would have degraded the user's experience. Prior work in 2019 showed that rotational jitter greater than half a degree degrades the user's throughput and increases user error in VR. However, this is not the case for static objects. Prior work showed that perfect registration of real and virtual objects are not required to maintain a high level of presence. Our pipeline overcomes this limitation by turning off tracking once gameplay begins and instead relying on other low jitter systems, such as the headset's built-in hand tracking to move objects. This slide shows several examples of jitter we encountered using continuous tracking. Positional jitter and a misidentified marker are shown in the top figure. Positional jitter is shown by the variation in the green normal vector, which we captured over a period of 1 second. The misidentified marker ID generates a false card. The bottom image shows the rotational jitter also captured over 1 second. Here the captured markers are shown superimposed on the camera far plane. Our tracker assumes that objects are stationary until a player interacts with them. Movement of passive haptic objects is accomplished using the Oculus Quest 2's built-in hand tracking and game mechanics. Cards start in a pile which is located by the tracking system before gameplay begins. This pile location remains static throughout the game. Cards are then interacted with using the Oculus Quest 2's hand tracking system. cards transition state when the user's hand intersects a pile, which is represented by the gray collision boxes in the top right figure. The state machine controlling each card is shown in the bottom right figure. The picked up card attaches to a fixed anchor point in the user's virtual hand. This attachment is delayed by 2 seconds, which we adjusted during development until multiple participants in our pilot study felt comfortable picking up a card with this delay. However, during our pilot study, some players were slow to pick up cards and could be confused by the card prematurely attaching to their hand. Once the player intersects their hand with another pile, the card leaves their hand and is played. Remotely controlled cards constantly update their position and attach to piles after being played by an opponent. We developed our user study to evaluate presence with and without using passive haptic objects. Here, users play a game of war against each other, which is a game that almost everyone knows and is simple. We chose this card-playing scenario to reduce the learning curve and complexity that could otherwise bias our study results. The study participants were divided into 2 groups. One group was provided with physical cards serving as passive haptic objects. This group had one-to-one correlation between movable objects in the physical and virtual environments. The control group did not use physical cards and instead relied on game mechanics and hand tracking to move virtual objects only. Our survey consisted of 12 standard questions from Whitmer and Singer's presence questionnaire. 23 participants took part in the survey. The results show a significant improvement in 3 measures of presence when using passive haptic feedback. On the 1 to 7 Likert scale, we found a 9/10 improvement in haptics and a 7/10 improvement in realism and the possibility to act. The box chart on the right shows the improvement in 3 standard measures of presence. Haptics in particular showed the best improvement because users can feel objects they are interacting with using their hands. This haptic interaction is also realistic and mimics how users would play cards outside of VR. Improvements in the possibility to act are due to the interface being more controllable and intuitive than relying on hand tracking and game mechanics alone to move objects in the virtual space. Our study also included a free-form questionnaire where users could write about their experience. We provided the questionnaire after users completed the survey to avoid biasing the results. This questionnaire consisted of 10 prompts. The responses were categorized to identify themes common across multiple users. These themes are gameplay experience, virtual and physical interplay, natural and easy hand interaction, and the sense of presence with others. Users also reported several factors that reduce their sense of presence. Game mechanics, such as the use of collision boxes and fixed pile locations, limited the user's sense of realism. Users also expressed an expectation for continuous tracking, which would have allowed players to hold more than one object at a time. Our static tracking approach, which fixes the location of tracked objects once gameplay begins, relies on the position of these objects remaining constant during the game. This includes the card pile locations. Both of these factors made several users feel the experience was less real. Continuous tracking would have allowed users to hold multiple cards at the same time with non-fixed positions in the hand, but tracking jitter would have degraded the user's sense of realism. Finally, I'd like to show a video demo. Here, two players are picking up cards, placing them, and progressing through their game of war together. You can see the local player is resting his arm on the table, which corresponds to a real physical table. The card pile locations correspond with real objects the user is actually picking up in real life.
1.
Thank you for your time, and I hope you consider adding passive haptic objects in your next VR application.